Okay, the second question for today is question 139, word break. We have a non-empty input string s and a dictionary word dig containing list of non-empty words. So both the words and the input string are non-empty. We don't need to worry about those as edge cases, which is good. We need to determine whether S can be segmented into a space-separated sequence of one or more dictionary words. Basically, given the input string S, we want to know whether we can stitch together the input with the words in the word dictionary. If we can do that, no matter which kind of combinations we have, we return true. If there is no any way of doing that, we return false. The number of ways or the number of possible segmentations or all the possible segmentations, successful segmentations, we don't need to worry about that. All we need to return is a true or false. So, two notes here. The same words can be used multiple times. That makes the question easier. The second one is there is no duplicated words. I don't understand why this is here. For example, we have Leetcode with the dictionary lead and code. We concatenating the two words to get Leetcode. For the second example, we have apple, pen, apple. We have the dictionary apple and pen. We just used apple twice, apple, pen, another apple. We can get apple, pen, apple. The third example, we have the dictionary cats, cat, and sand, dog. We have input string, which can be segmented in two different ways. From left hand side towards the right, we can do cat, sand, OG, or we can do cats and OG. Whichever case, we are left over with OG here. There's simply no way we can construct OG with the dictionary here. So just based on the intuition from manually working through the third example, we can see that we basically can, once we segment a word out, the remaining string and the dictionary, it's a smaller question of the same, it's a smaller problem of the same type, right? So once we break cat out, we actually just doing word break on sand OG with the same input dictionary. So this leads us to a recursive method of solving this. We just backtrack recursive method. So at the location in the very beginning, we try to segment one word out, and for whichever choice that we make, we do a recursive call on the remaining string with the same word dictionary. And just keep doing that until the very end. We have OG with the dictionary, with this word dictionary, because there's no way we can return a true here. We reconstruct OG with the dictionary, we return a false, and just pass that, backtracking that up to the very beginning level. And yeah, basically it's a backtracking recursive call to the same problem of a smaller size. If we don't use memorization, the time complexity will be in the exponential area. But if we use memorization, like determining whether OG can be breakable or not, if we catch those information, we can reduce that to to quadratic, I guess. But I don't like to write a recursive method for coding problems. We will think about something that's more iterative. So we want to go through the string once, right? And depends on we want to look into the future, or we want to look back. We have two possible similar strategies, but both of them we use the based on the recursive method, backtracking recursive. We see that if we can memorizing what can be breakable or not, it will speed up the the algorithm. It's the same thing with iterative method. We use an array of same size +1 with the of the size of the input string, we're just indicating can we do word break until the location. Like for this particular input, we will have 0011 00100. That's the one you know this is the input string, and the can break this memory, this array is going to be 0 0 oh no, it's going to be 1 0 0 0 0 1 1 0 0 1 0 0. So the initial 1 true is the base case, meaning that we can always do word break on an empty string because it's empty, and we can do cat, we can do cats. The D here means that when we look back, if we look back, we find we can do cat here, and we do have a send, so we know that the D, the location where D is at, we can apply word break with the string from the beginning to including D here. And or alternatively, we can, because we know cats is separable based on the 1 here, and we do have an AND, so we can use the other method of the other pass to get the conclusion that we can break cat sand, the string from the left, including the location for D. When we look at G here, we look at the previous 1 location. There's no way we can construct anything. We can use the word to get this. There's just no way. So we can look to the left when we are at a particular location in the iteration, or we can standing at the location of cat here, we find we have a sand, so we just flag the location D here. So just try all the words and flag those in towards the right to be 1. That's another way. So yeah, I'm gonna code the 2 solution up, 2 versions of the iterative method. One is looking towards this left, and the other one is looking into the future. They're pretty similar, but the time complexity is slightly different. Let's do the forward thinking kind of version first. So what we would do is to initializing this array what can break. For location, we enumerate iterate over all the locations, and if the current location we couldn't even break, then there's no way that there's no need we look forward, right? Otherwise means that we can reduce the problem size to be smaller, because we can segment the prior part up until this location. What we will do is try all the words that we can at our disposal. So we mark the future location to be 1 if we can segment another word out. In the end, we just return whether we can do that for the very last location. If that's the case, we have a method of doing this, applying word break on the whole original inputs. So that's one of the possible forward-looking iterative method. Okay, loc. Okay, so the time complexity is you can see that this outer loop is order of n with a number of words, and the number of the length of the input string. And this is order of let's just call it k, size of word dict. And this comparison is order of n, maybe the average maybe average length of words. So the total time complexity will be nkl. That's the worst case, right? So that's the forward-looking method. Let's look at the backward-looking iterative method, which is actually quite simple, quite similar. It's just we look back for those locations we can apply word break, meaning that we can break the question into smaller questions and try to see the gap between my current location and the last breakable points, whether that chunk of the string is actually a word in the dictionary. So instead of iterating over all the possible words, we try to see the gaps between the location and the previous breakable locations. We try to do this checking whether that's a known word or not. So for loc in range 1 and plus 1, for last loc in range location, if the last location is not breakable, we can skip this iteration. Otherwise, we check whether the difference in, the difference in between is actually known words in the word dictionary. If that's the case, we mark this current location to be true. So to facilitate this checking, we might convert this into a set. Yeah. So this will be a backward-looking iterative method. This one is order of n, and the second loop is order of n as well. So the whole thing is n squared. So it depends on whether the k and l, the size of k and l, either way might be faster. Depends on the the nature of the input problem. We can try to submit this one to see whether it's right or not. Yeah, it's working as well, and this one is actually slower, but the difference is quite small. So let me try to see if I can minimize myself a little bit. Yeah. So the difference is not too much, 72 and 60. So yeah, I guess the words and the average length is actually smaller than n in the worst test cases you have. So the forward-looking method, iterative method, is actually faster. So that's the question for today. Bye for now.